Yeah. Fallon? Yeah. Well, it'll say if someone's trying to join. Okay, so last time we were just talking about how to do some of the basic operations in the permutation group, right? So let me see here. So I think this is where we started, right? So we had this one permutation alpha, and then I showed you guys how you could write it in cycle notation and the array form. Most of the time we're going to be using this cycle notation. Then we did the same thing with this beta, and right now I'm just trying to show you how to compute, how do you actually compute products in this group, which is function composition, right? So I showed you this in array form, but in cycle notation, this is, in the long run, this is going to be the best method because we'll have to write the least amount of things, but we should just make sure that it's pretty clear how this works. So just to recap, so this is alpha in cycle form, right? Alpha was 1, 2, 4, and then this one cycle of a 3. So there's alpha, and beta was 1, 3, 2, 4, right? 1, 3, 2, 4. Okay. So in order to compute the product, the way that this works is you're going to write the answer in cycle form. And the very first thing you write is an open parenthesis. And then you start with what is the smallest number that you have not written, which will always be 1 at the very beginning. So 1. And then the way that what you're trying to do is you're trying to figure out where 1 goes via this function. And the way to do that is you read it from right to left. So the way I start to think about this is you take the 1, and this is sort of, as you're moving along, you have sort of currently what is your number, and at the very end, whatever your current number is as you sort of escape on the left side is what you'll write over here. So currently I am a 1, and I'm going to enter a cycle moving right to left. I'm going to enter the cycle if it has a 1 in it. So I'm looking right now for a 1. Right now I'm looking for a 1. And I do not have a 1 in this very first cycle that I encountered. There's only a 2 and 4. So I'm going to completely skip that. And I'll go to this next cycle, which has a 1. Now, within this cycle, 1 gets switched to 3. And now I update what is my current number. It's no longer 1 because it has been switched to 3. So my current number is a 3. And I continue to the left using the same process. So I'm looking for a 3. I find a 3. I enter. But I'm a 1 cycle. So 3 is going to go to 3. I exit. And I'm still a 3. So my current number is still 3, and I'm moving to the left, looking for a 3. I do not have one in this cycle, so my current number is still 3, and I come all the way over here, and that's what I'm going to write here. Okay, so that's the thing that you got to get used to. Well, let's do the exact same thing again with 3. So you know what? Maybe just for the sake of being able to write that process one more time, let me just copy here what we actually have. 1, 2, 4. Yeah. 1, 3, 2, 4 equals, so it's 1, 3. So I'm just, normally you won't have to do this. You'll just write the numbers and you'll be done. But because it's the first time we're doing this, let's figure out what the next number would be. Okay. So now you're going to start with 3. And your current number is a 3. So I'm looking for a 3. I do not have it in this first cycle, so I'll completely bypass it. But now I enter, and 3 gets swapped to this 1. Okay? So you're going to exit with this 1, and your current number is now a 1. So I'm looking for a 1. I do not have a 1 here. So I'll pass that one over, but I have a 1. And 1 gets swapped to 2. So now my current number is a 2. And that is what I'm going to write next. 2. Okay. All right. Now I'll probably write the rest of this without writing out all these arrows, and maybe we can just try to figure this out. Okay. So at the moment I have 1, 3, and 2. Okay. So my number is a 2, and reading right to left. So I'm currently a 2. I will enter this cycle. 2 gets swapped to 4. So now I'm going to exit with a 4, and I'm currently a 4, looking for a 4. There's no 4 there. There's no 4 here. There is a 4 here. So I'm going to enter, and the 4 gets switched to a 1, which is the beginning of this cycle. So now I exit with a 1, and I'm currently a 1. Normally, I would write the 1 right here, but because 1 is at the beginning of this cycle, to designate that I'm going to, instead of writing the 1 there, you just close off the cycle. And that tells you that 2 goes to 1. Okay? Remember that this means 1 goes to 3, 3 goes to 2, and 2 goes to 1. So you kind of have this cycle. Okay? So now you're not done yet, because if you look over here, I have 4s. But so what is the smallest number that I have not written yet? So I have a 1 here, a 2 here, and a 3 here. So the smallest number is a 4. And so you start with a 4, and you go from right to left. You're looking for a 4. That gets swapped to a 2. My current number is a 2. I'm looking for a 2, looking for a 2. Here it is. That gets swapped to a 4. I exit with a 4, and I'm still a 4. So really what that's just saying is 4 is going to go to 4. Okay? Now you could write 5, 6, and 7, but I don't have any 5, 6s, or 7s here, so they're basically not used, right? Now in this group, it actually was S4, so I'm really only going to use those 4 things. But keep in mind that you could, any element in S4 would also be an element in anything larger than 4. You kind of would tack on all these 1 cycles. But in the end, this is actually the answer. Okay, so this right here is alpha times beta. Okay, so this is alpha times beta.
Is it possible for, let's say the 4 got mapped back to a different number in that first cycle? Would that just be part of it? Probably have to be part of that cycle if that were the case.
If you did that during this simplification process, what that actually would mean is you must have made a mistake, actually, because over here, the goal, what you're actually doing here is you're simplifying it to the point where there's not going to be any repeats, meaning there won't be, like, you know how over here, if you look over here, I have 1s here and here, and I have 3s here and here, and I have 2s here and here, and 4s here and here. These are what are called, over here, these are called disjoint cycles, meaning they do not share any elements. So notice that these are disjoint cycles.
So they're not disjoint.
They share no elements. And these are, do you notice that these are not disjoint? Because, for example, they share 3s, they share 1s. These 2 are disjoint, this one and this one. And actually, this one and this one are disjoint. But altogether, it wouldn't be disjoint. So this whole process of simplifying what this is actually always going to produce disjoint cycles. So you should never have any repeats over here. Okay? It doesn't mean that they're not actually equal. It's just if you're following our process, there's no way that that would happen. Yeah, you'd always end up with distinct cycles over here. Now, one thing that we should take a look at is this is alpha times beta. Let's see what happens if we compute beta times alpha. Okay. I think it'd be a good idea to look at that. And yeah, it won't be the same. This group will actually be another example of a non-abelian group. So this right here is beta, right? And alpha was 1, 2, 4, and that 1 cycle. Remember, I also mentioned that 1 cycles you're not actually required to write, so you could just write this. Okay, because the 1 cycles don't really tell you anything. It's always going to map 3 to itself. So following this process, you see up here at the beginning, when I got to this part where I'm currently a 3, and you see that it pretty much would just pass over this 1 cycle, regardless if it is a 3 or is not a 3. If it was a 3, you'd enter it and exit it as a 3. But say you were a 4, you would not even enter it, right? So if those 1 cycles don't do anything. Yeah. So they're not necessary to write, but I wrote them in just for completeness. Okay, so starting off with 1. So I'm looking for a 1. Here it is. 1 goes to 2. So now I'm looking for a 2. 2 goes to 4. So now I'm looking for a 4. Okay, so I will write a 4 here. Did it just say someone was trying to enter the room? Hang on a second. Oh, actually, no, someone left.
We're lonely now.
Well, hopefully everyone that's not here will watch this lecture, because this was one of the more confusing things to me when I was trying to learn this. So far, are you guys okay? Yeah. All right, so start the whole process over again with 4. So 4, I'm looking for a 4. There's no 4 there. Here's a 4. 4 goes to what?
1.
Yep, 1. So now you exit. So keep in mind when you enter a cycle, you're going to do that operation once and you will immediately exit. You won't do it like more than once. That's the common mistake people make. So if you enter, you swap to whatever it is, and now you exit and you're currently that number. So now I'm a 1, looking for a 1, no 1 there, but there is a 1 here, which will switch to a 3. And now I'm currently a 3, which I'll write here. Yeah, exactly. That actually is exactly what it is. You're moving right to left as function composition. Yeah. It's just that this notation is completely new to you. So I'm just making sure that this is clear. Yeah. I mean, if you looked at, yeah. And then, so 3 goes to 3. Looking for a 3, there's no 3, no 3. 3 goes to 1, so I exit. Now, instead of writing the 1 here, because it's at the beginning, I'll close off the cycle. And then here is where you would start a new one, and you would say, okay, what is the smallest number I have not written? So I have 1, and I don't have a 2. So 2 would actually be the beginning of the next cycle, right? So now I'm looking for a 2. 2 goes to 4. 4 goes to 2. So I'm at 2. So this is actually going to be a 1 cycle. Okay, so these are disjoint cycles. Now, I did mention that these 1 cycles don't really matter, so I could just write 1, 3, 2 for this, and I could just write 1, 4, 3 for this. And, well, the important thing is notice that alpha beta is not equal to beta alpha. So in general, this actually shows you, this is an example that proves S4 is not abelian, because these are elements of S4, and you just showed there exists a pair that I could take a product and I don't get the same thing in either order. So in general, S4 is not abelian. And then in general, Sn for n greater than or equal to 3. For n equal to 1 or 2, they're trivial. Those ones are abelian, but for n is greater than or equal to 3, Sn is not abelian. And I think that that'll be a homework question for you for proving S3. Do you see that this example actually also proves that S5, S6, and S7 and so on are not abelian, because these are also elements in those groups, because I could just tack on 1 cycles. Like I could tack on a 1 cycle with a 5 and a 6 and a 7 and so on. And Sn for n greater than or equal to 4, right? But it turns out that S3 is also not abelian. So I think one of the homework questions, can you just come up with a counterexample for me in S3? S3 is only going to have 6 elements. It'll be 3 factorial is 6 total elements. So you could write out all of the elements and you could pick 2 of them and show me the product. You're just trying to find a counterexample. Just find a product where either one won't be the same, right? Same idea. Okay with that? So that'll be a homework question, I believe. Okay. So this is how you take products. So it's not really a proof that it's closed, but in general, if you are able to take this form and produce a new function, it's pretty much saying function composition from a function from A to A to a function from A to A will produce a function from A to A. So it is a closed operation, this function composition. Next question would be, what is the identity in S4? Well, these are all functions, right? So you have to come up with a function that would behave like the identity. So what is, oh, just trying to enter. All right. Yeah, you know what, let me change the settings to the room so that way, just disable the waiting room. That way nobody has to do that again. Okay, so what is the identity in S4? Okay, well, this will actually just be, you could denote it as E or epsilon. this will just be the identity function. Whoops, that's not the identity function. So 1 will go to 1, 2 will go to 2, 3 will go to 3, and 4 will go to 4. Okay. And what will that look like? Well, that'll look like, well, 1 will go to 1, 2 will go to 2, 3 will go to 3, and 4 will go to 4. You could, so this is kind of the one instance where, you know how I say you don't have to write 1 cycles? Well, if I just wrote empty space, it's kind of hard to see that the identity's there. It still behaves well if you think of it that way, but I guess in this case, maybe just write one of those 1 cycles. Okay. And you could check this, right? If I take any function and I compose it with that thing, it's going to give me back the function because that 1 is not going to, these are not going to swap any of the elements. Okay. And how do inverses work? How do we take inverses? Okay. Well, if you look at this in array form, all you have to do is you have to figure out where 1 gets sent to and so on. But if you look back at how we define beta, right? Beta was 1 gets sent to 3. So the inverse should send 3 to 1, right? Should do the reverse. 4 should get sent to 2, 1 should get sent to 3, and 2 should get sent to 4. So you sort of, in array form, it's kind of easy to just look at it and just figure it out. So 3 would go to 1, right? 3 would go to 1. 4 goes to 2. 2 goes to 4, and 1 goes to 3. 2 goes to 4, 1 goes to 3. Okay. So,
That's actually doing the same as
yeah, it does. Yeah. So let's write that out actually. So you'd have 1 gets mapped to 3, 3 gets mapped to 1, so we close that. 2 gets mapped to 4, 4 gets mapped to 2, so you close that. And now you can check what is beta times beta inverse. So this will be 1, 3, 2, 4 times 1, 3, 2, 4. They are actually the same. And we can just check, okay, 1, start with 1. 1 gets mapped to 3, and then 3 gets mapped to 1. So you close that off. 2 gets mapped to 4, 4 gets mapped to 2. So we close that off. 3 gets mapped to 1, 1 gets mapped to 3. And finally 4 gets mapped to 2, 2 gets mapped to 4. So you see that this really is the identity here. Okay. And similarly, alpha inverse, you could look at alpha, 1, 2, 3, 4. Okay, 1, 2, 3, 4. 1 went to 2, so the inverse 2 should get sent to 1. 2 should go to 1. 2 goes to 4, so 4 goes to 2. 3 goes to 3, so 3 should go to 3. So that one doesn't change. 4 goes to 1, so 1 should go to 4. And in cycle notation, this would be 1 gets mapped to 4, 4 gets mapped to 2, 2 gets mapped to 1, so we close that off, and 3 goes to 3. Now this is not actually the same as alpha, right? Alpha was 1, 2, 4, right? So 1 goes to 2, goes to 4, goes to 1. This is 1 goes to 4, goes to 2, goes to 1. All right. So, we could check it if you want. So 1, 2, 4, and 1, 4, 2. Look, 1 gets mapped to 4, which gets mapped to 1. 2 gets mapped to 1, which gets mapped to 2. 3 gets mapped to 3, gets mapped to 3, gets mapped to 3, blah, blah, blah. And then finally 4 goes to 2, 2 goes to 4. So this is also the identity. Okay. Now, I haven't really shown you how to take the inverses, though. I'm just showing you in array form, right? So we still need to figure out how to do it in cycle form, which I'm going to show you in the next note set.
So you should be able to do the inverses in either order, right? Like you want to do alpha inverse times alpha.
Oh, yes, yes. This should be the same in the other direction as well. If it is truly the inverse. Yeah. Which, since these are functions, it is good to double check in both orders. Yeah. So, you know how we did say that this group in this example here, that here's a counterexample to it being abelian, right? You actually showed alpha times beta is not the same as beta times alpha. So that shows the group is not abelian. There may be elements that do commute with each other. So for example, here, alpha and alpha inverse are actually distinct elements, but they actually do commute with each other, right? They happen to, when you take the product, you happen to get the identity. So that's true in general. If you're in a group, an element will always commute with its inverse, right? So if you were to compute, we called it the centralizer of a specific element. You fix an element, the elements that commute with it will always be, you're always guaranteed, well, 3, but they might not be distinct, okay? Do you know what they are? If I handed you, let's say this element alpha, I claim that there are definitely 3 things that commute with that element, but they might not be distinct, okay? One of them is the inverse. One of them is, you guys want to make a guess on the other ones? Or maybe anyone online?
The identity?
Yeah, the identity, right? If I took alpha times the identity, that would be identity times alpha. And then the last one is sort of a silly one. It's itself, yeah. Because alpha squared is, a times a is alpha squared, which is a times a, right? Now, they all might be the same element. Like, for example, the identity is its own inverse, and it is the identity. So, see, but if you're in a group where you're talking about a non-trivial element, it might have an inverse that's not the same, and it might not be the identity. So they could, you might end up with 3 distinct things there, or as small as just 1. So far, okay? Okay, now from now on, it is going to be very rare that I will use this array form, because you'll end up writing a lot more than using the cycle forms. So in the next note set, which I just actually updated minutes before the class, I did update this on the Blackboard page. The only thing I did was I actually just added this first page here, okay? And so you guys picked it up? You good? Okay, now I did mention this last class. So let's say that you have an element of Sm, okay? M could be any integer greater than or equal to 1, okay? But for this definition here, probably n here is going to be less than or equal to m, right? I just wanted to call it an n cycle, so that's why I temporarily switched it to Sm. Okay, so a cycle has this form, all right? I can have elements in my permutation group that don't look like this, but they are built from things that look like these, okay? So this is called an n cycle. So for example, what would a, okay, so here's a 1 cycle. This is a 1 cycle, okay? It's a cycle of length 1. 1, 3 is an example of a 2 cycle. So you see, what this is telling you is that 1 goes to 3 and 3 goes to 1. Okay, it's a cycle of length 2. Okay, this is actually also sometimes called a transposition. I think that's how you spell transposition. I think it might be on the next, page. Yeah, it's on the next page, but that's okay. We'll come back to that. It's just called that because all this is telling you is that those elements swap with each other. If you want a visual diagram in your head, if you want a picture, I'm rarely going to have you think about the picture, but the picture for the 1 cycle is like you have a 1 and it's just getting mapped to itself, but it looks like a cycle, right? 1 gets mapped to 2, or 3, sorry, and 3 gets mapped to 1 would be the visual for this 2 cycle. Let's say that I had 2, 6, 7. This would be a 3 cycle. Okay, so the term n cycle is just telling you how many distinct elements you have in this representation, but it is telling you how the function is interacting. So this is kind of telling you that 2 is going to get mapped to 6, which is going to get mapped to 7, which is going to get mapped to 2. Okay, and now the visual of why you might call that a cycle makes a little bit more sense, right? It's kind of telling you as a function how it's behaving, right? Now, not every element of Sn or Sm is going to look like this, right? But it will be built from these cycles, right? Every single element has to get mapped somewhere, right? In a bijection. So, so notice, how about I give you a non-example, okay? Let's say that I have 1, 3, 5, and 2, 4. Okay. Now, this thing is not an n cycle because it's built from 2 individual cycles. You see that? But is the product of a 3 cycle and a 2 cycle. So it still has structure that is built from cycles, but it is not itself a cycle. Okay. These are disjoint cycles. Okay. So like this thing, you could say that this is your 3 cycle and this is a 2 cycle. You guys okay with that? Now, it is difficult to actually tell if I just arbitrarily gave you something like that, if it really is an n cycle or not, until you simplify it to the point where you have disjoint cycles. Looking back at our example that we just did here, I'll wait until you're done writing that. Let's see if I got any water. Okay, just looking at that alpha beta calculation that we did, right? If you just look at this, it's deceiving that you might say, oh, that thing is not an n cycle, right? But you actually can't say that it is or is not until you simplify to the point where you have disjoint cycles. Notice that I have overlaps. I have 1 and 1 here and so on. So I haven't really simplified that yet, but after simplifying it, do you see that this actually ends up being well, it's a 3 cycle times a 1 cycle, but the 1 cycles you ignore, those don't prevent it from being an n cycle. Do you see that this actually is a 3 cycle? And that's not clear from the beginning. Like you won't be able to classify it until you could simplify the whole thing. Okay. So if you ever end up with something where it is, it's like let's say it's a 3 cycle times a 1 cycle, the 1 cycle you would just ignore and you could still call the thing a 3 cycle. Okay, and so on, right? So I don't think I need to give you an example of like a 17 cycle, but you could generalize this. All right, now the easiest thing to take inverses of are n cycles, because actually the inverse, all you actually have to do is, if you look at this, a1, a2, an minus 1, an, to take its inverse, all you actually have to do is just create a cycle, but go in the exact opposite order. Okay, it's very simple. So for example, inverting these guys up here, well, the inverse, this is the identity. The inverse of that is just itself. The inverse of 1, 3 is 3, 1, but this one is a weird one because this actually is also itself. You see that?
Oh, yeah.
Okay. Now, but the inverse of, let's say 2, 6, 7, this is just 7, 6, 2. Okay. And if you draw the visuals over here, you see this one was 1 goes to 1. Well, the inverse should also go 1 goes to 1. Okay. And if you had 1 goes to 3, then the inverse should also be 1 goes to 3 and 3 goes to 1. Right. The inverse of this one, 2 goes to 6 goes to 7 goes to 2, should be, the arrows should go the other way, right? The arrow should go 7 goes to 6, goes to 2, goes to 7, right? 6 goes to 2, right? 2 goes to 7, 7 goes to 6. So you see, it's just the arrows are going in the opposite way. So whatever the cycle direction is, the inverse should go in the opposite direction. That'll make sure that everything correctly goes the other way.
So even with the product of the 2 cycles there,
Mhm.
1, 3, 5, and 2, 4, can't you still, the inverse of that, wouldn't that still be
Yes.
each individual one?
Yeah, that's what we're going to do down here. So once you understand how to take inverses of n cycles, you can take inverses of arbitrary elements because we have that socks and shoes thing. Remember? Yeah. So you just do socks and shoes, or the generalized version of it, and then you just use this this method for each cycle. So it's actually really easy. Once you have it as the, well, actually the funny thing is you can use this formula even if they aren't disjoint. Yeah. But most of the time you probably would simplify it until they're disjoint anyway. Because if I was going to ask you a bunch of questions, that's usually one of the first things you do anyway. Yeah. Yeah. So are we okay with this? One thing you'll notice this is the same as itself and same as itself. And this is not the same. Okay. Transpositions have this special property that two cycles are they will always be their own inverse, because if I take a two cycle and write it in the opposite order, that actually is going to describe the same function. Okay. So two cycles or transpositions have this special property that their inverses are themselves. Okay. Like in general, it would look like this. If I have A1, A2, A1 and A2 can be any numbers you want. The inverse of that will be A2, A1, but that is actually the same as A1, A2. Okay. And if you just had A1 inverse, that is itself. But once you go up to size 3 or more, that's not the case anymore, right? They're going to be distinct. Okay. I'm just pointing that out because that's actually a very special use. It's actually a very useful property. But that's only true with transpositions. For size 3 and so on, that will not be the case. Okay. So inverses of arbitrary elements. Now, if you're an SN, I'll denote an element of SN with this sigma, and you could write it. You can always write an element as a product of cycles. Okay. So each alpha I is a cycle. Alpha I is let's just call this an L cycle. Okay. Each of those might be of different length, right? So that's why I had to give it another parameter, I guess. I don't know. I guess you could say it's L sub I, right? Where it would depend on the I. Okay. Like the first one might be a 6 cycle, the second one might be a 2 cycle, the third one might be a 5 cycle, so on and so forth. Well, all you got to do to take the inverse is take the inverse of a product of cycles. And you had that homework question. Do you remember I had you prove that in general, socks and shoes was if you take the inverse of 2 elements, you just swap them and then invert them, right? But they got to be in there. You get swapped. Yeah, that's exact. But you proved using induction that socks and shoes generalizes to n elements. And that's what we're doing here. So we have k elements, right? K of these products. To take its inverse, you just rewrite them in opposite order. And now you would just use this formula I just showed you. Now use formula above. Okay. So let's just do that in action, right? So for example, I had this element here. Let's try to take its inverse. So let's say I had 1, 3, 5, and 2, 4, and I asked you to take the inverse of this thing. Okay. Well, in order to do that, you are going to take these cycles and first write them in opposite order and invert. So it'll be 2, 4 inverse, 1, 3, 5 inverse. Okay. So that is you could say by socks and shoes. We okay with that? I'm not writing it here, but it's not a bad idea to write it so that way I know what in the world you're actually doing. And then now using the formula up above, these are n cycles, so just write them in descending order instead of ascending order. So this one would be 4, 2, which is actually going to be the same thing as 2, 4, because that's a transposition. And then this one would be 5, 3, 1. And honestly, that's it. And that's your answer. Yeah, I always liked it. I can't remember if the book calls it that. They should though. So much sense. Yeah. Yeah. And you guys can check this. And I mean, if you think about it, if I just had alpha 1 up to alpha k and I multiplied by this gadget, they're going to individually collapse, and it would end up working. But if you want, you could check it. Maybe I'll just do one other example real quick. We could just make up a cycle if you want. You guys have any favorite numbers? 9, 6? Okay, and maybe another cube or another, let's say 4. Now, even if these aren't disjoint, you could still do this process. So, I mean, these actually are disjoint, but if they're not disjoint, you can still use socks and shoes and so on. So the inverse of this whole thing would be 9, 6, 4, but invert, and 7, 8, 1, invert. And this would just be 4, 6, 9, and 1, 8, 7. Okay. And if you ended up with something and then you wanted to figure out if it wasn't disjoint, then you could simplify that to its disjoint cycle form if you wanted to. Okay. So again, this is by socks and shoes. Okay, so on. Okay. The reason I actually wanted you to get used to using socks and shoes is in the event that they were not disjoint, you absolutely would have to do socks and shoes. What's funny is actually if they are disjoint, the cycles do commute with each other. So you're not actually you're not required to use socks and shoes if you know the original is disjoint. But I just wanted to get used to the process in the event that you just sat down, started doing some of these calculations and didn't think about things, right? Yeah. It's better to just get into the habit of it because you're making fewer assumptions, right? Yeah. Okay. So just keep in mind, this works even if you are not disjoint. In fact, that is the only way you could do it is by socks and shoes. All right. All right. Okay, next. I kind of have already defined this, but I'm just writing it out for you that suppose that you have 2 cycles, right? This is not arbitrary elements. This is actually, they are in the form of 2 cycles, right? So sigma and tau here are elements of Sn, and suppose that sigma, it looks like that's a K cycle, and this is an L cycle. K cycle. This is an L cycle. So this definition is not going to apply to everything in Sn because Sn may contain elements that are not just K cycles or L cycles, but you can generalize the idea. And we say that they're disjoint if they don't share anything, right? If there's no alpha I that's equal to some element over here, okay? And then this theorem is kind of nice. It just says like if you happen to actually have disjoint cycles, they do commute with each other. So the argument for that is not shocking because if you think about how we simplified those functions, you're only going to enter a cycle if you are that current element, right? So if it's before it or after it and your current element is not involving anything in that cycle, you're just going to skip over it anyway. But we could just do an example. Yeah, here's a good one. Okay, so let's say that I have 5, 6, and 1, 2, 3, 4. So these are disjoint. So they actually do commute. Okay. There's no 5 over here, there's no 6 over here, and vice versa, right? So this is actually equal to 5, 6, 1, 2, 3, 4. I just wrote the same thing. Not that that's false, but that's not interesting, right? That's the interesting thing. I think because it's so warm out, might need to get some water. Right? Yeah.
Will we ever have to prove that theorem?
The proof of it's pretty short because if you just think about function composition, if I was going to input an element, right, plug it in, if you just think about what the output would have to be relative to the two compositions, I mean, if you're sort of simplifying this whole process, right, it's kind of natural that, like if I'm starting this simplification process, none of the outputs are going to be anything that's over here. So I'm never going to update the current status using this cycle. So it doesn't matter if this cycle is over here or over here. The proof is in the book. It's theorem 5.8. You can look at it. It's relatively short. It's pretty short. I wouldn't ask you to prove that. This is just a nice property. I like permutation groups because a lot of problems I can create are sort of these nice computational problems. And we will prove certain things, of course. It's just we're going to be looking at structural things that we can prove. All right. The proof of that is actually pretty short, and I encourage you to try it. It's not that long. One of these proofs is quite long. I'll show you that in just a second. So every element of Sn can be written as the product of disjoint cycles. And how you actually do that is just the normal simplification process. The how is more important because that's what you're going to be doing more often. Okay, so the just simplify as we have done. Okay, so for example, let's say that I have 1, 2, 4, 2, 3, 5, 6, right? These are definitely not disjoint. Do you see that these two cycles have a 2 in them? Not disjoint. They share a 2, right? So what this theorem is claiming is even if you have cycles that share something, you should be able to simplify it to disjoint cycles. And the way to do that is just simplify it as we have done. Okay. So how would you rewrite a product? Well, you start by writing what's the smallest number available that I haven't written, which will always be 1. If you're talking about Sn here, your elements are 1 up to n. So 1 is not in here or here, but it goes to 2. So I will update this now and write a 2. 2 goes to 3. My current number is a 3. There's no 3 here. So I'll exit and write a 3. Now I have a 3. 3 goes to 2. 2 goes to 4. So I'll write a 4. 4 goes to 1. So instead of writing the 1, because it's at the beginning, I'm going to close this off. Right. Always check the beginning. Right. In this case, I was looking for a 1 because I was simplifying that. But when you're doing these things in general, always make sure you look at that first number again so you don't rewrite it or skip over it or something. Okay. And then the rest, well, the smallest number I haven't written is 5. 5 goes to 6. And then 6 goes to 5. And so you get this. Okay. Now these are disjoint. Okay. Let's just take, can I just take like a couple minute break real quick? I just want to get some water.
I want you to pass out up there.
Yeah, right. Usually I have something with me, but I think I forgot to bring some.
Yeah, you're right there here. So.
Yeah, it's pretty warm right now.
You're doing teaching, right? No, I'm just a general math track with computer science. You hate computer science?
Yeah, I hate it so much.
Yeah.
I'd like to do it like on the side, I guess. I don't want to take classes.
Yeah, I was originally going to come here, I was going to be just a math major. I was going to focus on actuarial science.
It's gonna be stats and then COVID had something.
I was going to add a stats track too, and then I took stats too and decided not to.
Yeah, I was gonna do stats. Then COVID happened, and I was online last fall, and I didn't want to take stats online.
I took it on my last semester.
I'm like, well, I don't want to do it. I was looking at biostatistics, but I don't know. I'm graduating in the fall and a lot of stuff, and none of these schools take
I am a junior.
Well, you don't have to take geometry here in topology, right? So,
Apologies, just taking as a elective.
Oh.
Technically.
did you already take geometry or?
No.
You're a math major though, right?
Yeah.
Well, one of the requirements is either you take geometry or topology.
Yeah. Well,
So,
there we go.
There you go.
Apologies.
Yeah, yeah. Well, you could still take geometry, but I would say only do it if you wanted to take it.
Yeah. Right. I don't know any geometry. Or maybe I just haven't put it on there.
You're gonna take an
I wrote that
elective.
whole plan last semester and then totally forgot about it.
Yeah, I just take what I think is interesting.
I'm also a comp sci major.
Oh, okay, cool. Are you in the data science course right now, by any chance? Okay, because I'm gonna be teaching a data science. I think I'm gonna be teaching a data science course next semester, but I'm gonna do it in Python, and I think they're doing it in R right now, which is almost perfect because business is doing theirs in Excel. So now we'll have a data science in almost every.
I got an email about it from most about an internship with our studios or something.
Yeah.
I've never even touched R. I've only
Yeah.
done Java and C.
Okay,
and Linux.
cool. Yeah, I'm gonna do that. It'll be actually at this time slot, I think, in the fall.
What is data science?
Well, okay, so you're you are taking tons of data, and the first thing you're trying to do is you have to clean the data up. And then what you do is you usually apply machine learning algorithms to try to extract some predictable information about that data. You know, like let's say, for example, Pandora or Spotify, right? They give you suggestions on what to listen to,
Based
right?
on what you've already listened to.
Based on what you've already listened to. So it inputs a bunch of these variables. It probably can approximate how old you are. And then it can-
generalize them into a specific
Exactly. So it's creating a correlation, and then it's giving you some suggestion based on that correlation. Like you may have never listened to this artist, but this artist correlates with these other ones very well.
Cool.
Yeah, and it's there's just a bunch of math behind the scenes going on.
Yeah.
And the cool thing is machine learning is you're kind of it's creating sort of these predictive outcomes without ever being programmed to actually do them, but it's just using the math to give you those suggestions. Yeah.
I take that, but I have to take 203 geometry and real too. So.
Oh, a little too many.
I usually stick with 3. I don't really want.
Yeah.
Because I know people that do like 5, and I'm like, I can't do that. I'm not that good.
Yeah.
All 5
But I'm gonna try to teach that.
Yeah, I'm a big fan of 12 credits a semester. I'm a big fan of that.
Yeah. Yeah, I mean, you can spend a lot more time on the courses for sure.
Because you're really trying to you're not trying to hack this, you're trying to learn exactly, that's all I see. I'm like, if I'm just trying to plan the path stuff, I need to drop class.
Yeah.
So I don't know, some people like to do 18 credits.
Yeah, I used to take way too many, and then I wouldn't have much sleep. So it's like you either want to hang out with your friends, or have you ever seen that triangle?
Yeah, the social life.
Yeah. So I was definitely I want to hang out with my friends and take a lot of classes, so I didn't sleep very much.
You took
Yeah.
the sleep right now.
Yeah. So yeah, it is what it is.
Yeah.
So there is actually one thing I wanted to mention here that I didn't add. I should have added this as like a little mini lemma here. So mini lemma. Once you get it into these disjoint cycles like this, you can actually use it to compute the order. Okay, so let sigma be an element of Sn. And if you want to compute the order, it's actually the least common multiple of the lengths of cycles in a disjoint cycle decomposition. Yeah. Lengths of the cycles in a disjoint cycle decomposition. So for example, this one right here, for example, the order, let's call this sigma. Okay. So the order of sigma in this example would be the least common multiple of just 4 and 2. So it's actually just 4. Okay. It's kind of interesting if you start to think about why that would have to be. And I suggest just trying it out with a bunch of examples. You might encounter that in the homework, actually. But what's kind of happening is this. If I had
Does these come multiple 4 comma sigma?
4 comma 2, because this is length 4 and this one's length 2.
So if
Yeah.
you had like 3 different cycles, you would have.
Oh, yes, yes.
you
So
would add in the least common multiple.
yeah, so 4, 5, 6, 7, 8. If this was, let's say this is sigma 1, right? These are disjoint, right? No, nothing shared. So the order of this would be the least common multiple of 3, 3, and 2, which would be 6. Okay. Let's just look at this one. 1, 2, 3, and 4, 5. So this one would also be just least common multiple of 3 and 2, which is 6. Okay. The reason for that is if you actually, I encourage you to do this. Compute what the square is, what the cube is, what the fourth is, what the fifth is, and what the sixth. Okay. The sixth should get you to the identity, but this would be a good problem to just try to get used to doing these calculations. Okay. But what you're going to notice is if I square this 1, 2, 3, 4, 5, and then times 1, 2, 3, 4, 5, we could do the first one together. Let's see what we would get. So 1 goes to 2, 2 goes to 3, so I'd write a 3. 3 goes to 1, and then 1 goes to 2, so I'd write a 2. 2 goes to 3, 3 goes to 1. So instead of writing a 1, I'd close this off. And then I would have smallest number that I haven't written is a 4, right? 4 goes to 5, 5 goes to 4. 5 is the smallest number I haven't written. 5 goes to 4, 4 goes to 5. Okay, so you could just write this as 1, 3, 2. Sorry, I should have made this smaller so you guys could see that better. Okay. Now, when you go to compute the cube, are you going to write this out 3 times? No, just write this once. 1, 2, 3, 4, 5, and then now take this answer and put it here because that's the same thing as this. That's the same thing as sigma 2 times sigma 2 squared, right? So now this you can put here. So I encourage you to figure this out, right? But look what happened when I squared this. Did you notice that the two cycles became the identity actually? Because their order, a 2 cycle has order 1, right? So when you square it, it'll be order 1. Oh, I guess I didn't actually say that. The order will be 2, right? Because if this is a n cycle, what's the order of it? It'll be the least common multiple of just itself, which is just n.
Okay, yeah.
Yeah. So a 2 cycle will have order 2, which is a transposition, because it is its own inverse. Like you square it, you'll get back. So notice the 2 cycle kind of got obliterated here, but then the 3 cycle stayed because that 3 cycle will actually have order 3. Right? Actually, you know what? Let's do the next one. Let's just do one more. Okay. So 1 goes to 3, 3 goes to 1. Okay, 2, right? Isn't that right? 1 goes to 3, 3 goes to 1. Okay. 2 goes to 1, 1 goes to 2. Okay, now 3. 3 goes to 2, 2 goes to 3. And then now I have a 4. 4 goes to 5. 5 goes to 4. So I actually get 4, 5. So check this out. When I cubed this thing, the original 3 cycle that's involved went to the identity, but now that 2 cycle came back. So you see what's happening is the 2 cycle, every even power is going to go away.
Oh, I see.
And every 3 power, the 3 cycle will go away. So the first time, you're looking for the first time that both of those will simultaneously go away at the same time. And that won't happen until the least common multiple, because it's got to be a multiple of 2 and a multiple of 3. See that? So I encourage you to try out the 3 and the 5, and you'll kind of see that. They kind of like disappear, reappear, disappear, reappear. And the only time that, the first time they will both disappear is 6. The next time will be 12, right? They'll both disappear again and so on. But the first time they both disappear will be at the least common multiple. Okay. So I guess you should say a mini lemma 2. You know what? Let's write that here, I guess. Mini lemma 2. An n cycle has order n. Okay, and you guys can check that. An n cycle has order n, and then if you have a general element, you can always write it as a product of n cycles, and then the order will be the least common multiple of each of those individual disjoint cycles. Okay, you have to first find a disjoint cycle decomposition, which we said always exists. We didn't prove it, but it does always exist, and then you can use it. Okay, definition, I kind of already mentioned this before, but a cycle of length 2 will be a transposition. And a 2 cycle is a interesting element type because, well, they are their own inverses, which is the same thing as saying that their square is the identity, and it is not the identity. Okay, if you say, you have to say both of those, but okay. Next theorem is showing you that not only can you actually take an element and write it in terms of disjoint cycles, but you can actually always take an arbitrary element and you can write it as a product of transpositions. You can always write it as a product of 2 cycles. So every element of Sn can be written as the product of 2 cycles or transpositions. And to do this, this is the trick that you use for individual cycles. So if you have a cycle of length n, to rewrite that as a product of 2 cycles, what you do is you do, the first 2 cycle will be the first and the last. Then it'll be the first and the second to last, and then the first to the third to last, and so on. Okay, let's just do a couple examples, and you'll see how that works. This one. So for example, we could just take the same exact one that we've been doing here. So for example, for this theorem, sigma again was 1, 2, 3, 4, 5, 6. This already is a 2 cycle, but this one is not, right? So I'm going to use the trick on this one. So the trick would be, it's 1, 4, so the first and the last, then it's 1, 3, and then 1, 2. 1, 3, and 1, 2. Okay. So the red there is the same as the red there, and the 5, 6 just goes along for the ride, so it's right here still. Okay. Notice that when you do this, you're not going to be disjoint anymore. So you sacrifice the disjoint decomposition for the fact that you rewrote it as a product of 2 cycles. Okay. So over here it's disjoint cycles, disjoint cycle decomposition. Over here, it is you call this a 2 cycle decomposition, 2 cycle decomposition, but not disjoint. Okay. So you might ask, well, why is that useful? Well, it's useful for a completely different thing. This is very useful for doing calculating usually, because it's much simpler to do calculations, and you can use that to calculate the order. Inverses are easier, and so on and so forth. Over here, you could use this. You could actually use this to compute inverses, which it would be pretty fast because they're all 2 cycles, but it won't be disjoint. This will actually be useful for something I'm going to explain in just a second. Okay, so it's just different. It's useful for a completely different thing. You want to do another example?
So the you couldn't calculate the order of that two-cycle decomp because they're not disjoint. Right?
Yes, yeah, I can't move these things. I could move the 5, 6 wherever I want because that's disjoint from these 3. So I could move the 5, 6 anywhere I want, but I could not move these ones around because it would build a completely different element. Yeah, it's a good question. So another example, we could just make up something. Let's say 3, 4, 5, 1, 8, 6, 3, 2. Now, even though this is not disjoint, I could still use this trick. There's nothing preventing you from doing that. You just use this trick on individual cycles. Okay. So notice that this is not disjoint, but I can still do the trick on it because all you're going to do is do the trick on each individual cycle. So for example, the red here would become first and then the last, first and the second to last, first, third to last. So this would still become this. And this cycle, this 4 cycle would become 8, 2, 8, 3, 8, 6. Okay. So neither of these are disjoint. So if you needed to compute the order of this thing, first you would actually probably simplify that into its disjoint cycle decomposition, which we could do. Okay. But it's not necessary. Although that might be interesting. Hang on a sec. Let me think of something real quick. Well, anyway, do we at least agree that we've rewritten this into a product of 2 cycles? Okay. All right. It might be interesting to actually look at that because, yeah, well, the reason I'm thinking it might be interesting is if you simplify this until it is disjoint cycles, and then I ask you, okay, use that to produce a 2-cycle decomposition, you might get a completely different 2-cycle decomposition.
I think you would.
Yeah. So, yeah. So, let's see what would happen. So if you simplified this into disjoint cycles instead, first you would have 1 goes to 3, then you have 3 goes to 2, and then you'd have 2 goes to 8, 8 goes to 6, 6 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So you'd close that off, right? 1, 2, 3, 4, 5, 6. So 7 is missing, right?
We don't have 7.
Yeah. So 7 would just go to 7. Okay. And then 8 is in here already, right?
Yeah.
So we know where 8 goes. So how long is this? 2, 4, 6, 7. Okay. Well, if you did this process with this guy, you'll get something completely different.
Sure.
But it'll actually, these are all actually equal, right? So you'd have 1, 5, 1, 4, 1, 6, 1, 8, 1, 2, 1, 3. Okay. So this is equal to this, is equal to this, is equal to this. And they may all be different, useful for something else. Now, these 2 different 2-cycle decompositions, what's interesting is, well, in this particular case, we actually ended up with the same number of them. There were 6 2 cycles. I was hoping that it would actually simplify into something else. There's a theorem I'm going to show you in just a second. It turns out that when you do this 2-cycle decomposition, you might not end up with exactly the same number, but you will end up with the same parity. So if there was an 6 here, there's an even number of them. So no matter what, I know I should end up with an even number down here. It may be 4, it may be 8, it may be 2020, but once you know that there's an even number of them, it would actually have to stay the same.
Now, what I'm saying is the order of that cycle is 4, right? Because
The order of this element will be, you could use this one because that's the one that, yeah, the order would be 7, right? because that cycle has length 7, right?
Yeah, that's 7.
Yeah, so this element, you'd have to,
So if you multiplied one of those by another one, and then by the other one, would you end up getting it to?
it won't be the identity there because so individual 2 cycles, when you square them, you get the identity, right? And the reason that happened with that one example we did was because things were disjoint. When you square them and they're not disjoint, they're going to interact with each other.
Okay.
So it's really
the
weird.
Order of those, they mean the same thing, but the order of those would be different.
This element here will actually have order 7. You'd have to take this crazy thing and multiply it by itself 7 times before you get to the identity.
Okay.
Yeah. It seems like that's defying the property that's 2 cycles have order 2, but it actually isn't because they actually, I mean, to get this order, you take the least common multiple of lengths in a disjoint cycle decomposition.
What I was saying is, like, if you were to multiply the first equation by the second one on the right.
Oh, yes.
Would that be the same as squaring it?
Yes, that will be the same.
So if you were to do that over and over again, you could still get to a identity, even though you're multiplying by one.
Yeah.
Looks like a different.
But the simplest one to do that with would probably be this one, right? So when it comes to actually doing the mathematical calculating by hand or using a computer, once you get it into disjoint cycles, you'll have the fewest number of calculations to do. Because this one has no repeats in it, so I already kind of know where each individual element is going. I don't have a combination of compositions and things like that, right? Like right here, this has so many repeats. Do you see, like, you're composing 6 functions that happen to tell you where 1 goes, where it's much faster over here to just say, oh, 1 goes to 3, 3 goes to 2. Yeah. So in terms of calculating, that one's the best. But in terms of extracting information, these other ones could be useful. Okay, now this is a theorem that is not trivial at all, okay? It seems like it's not that crazy, but this one says if you write the identity as a product of transpositions, which we know you can do by the previous theorem because you could just do that trick, the identity, if you write it as a product of transpositions like this, it turns out that the number of transpositions must always be even, okay, for the identity. So let me give you an example. Well, the identity, here's the identity, okay? Here's one way to write the identity. That is a 2-cycle decomposition. There's only 2 cycles here, if you kind of think about it, right? You could just think of it as blank space. There's 0, 2, 0, 2 cycles. And do you agree that 0 is even? Well, let's do a non-weird example. Like, what about 1, 2 times 1, 2? Do you agree that that is, well, 1 goes to 2, 2 goes to 1, 2 goes to 1, 1 goes to 2. So do you agree that this is 2 cycles, right? 2 cycles right here. So this number, do you see that is even? And this is even. Right? I could also write the identity as 1, 2, 1, 3. Oh, you know what? We might have one at the beginning, but I think everything was repeated there.
You can write the identity as any inverse, right?
Yeah. Yeah. Well, it's just saying that any 2-cycle decomposition you could possibly come up with for the identity, no matter what, the number of 2 cycles in that thing would have to be even. Right? The proof of that is not very obvious. There is a very, very clever proof that is done in the book for that theorem right there, and I encourage you to look it up. But what's cool is once you know this is true for the identity, you can prove it for all the other elements. And that's what the follow-up theorem is. The follow-up theorem is saying if sigma is an arbitrary element, okay, and you write it as a product of 2 cycles, this time tau 1 up to tau r, if it turns out that r is even, then any other representation as a product of two cycles, there must be an even number of two cycles. If it turns out that the R that you found is odd, then any other representation must also have an odd number. And the proof of this is actually not terrible, because all you do is just suppose you have suppose sigma equals tau 1, tau 2, tau r. And these are all two cycles. And suppose you have another two cycle decomposition. Can you think of another, I don't know, let's use Q's, Q1, Q2 up to Qs. And these are all two cycles. How do I make use of the fact that the identity has always an even number? Is what I could do is I can take sigma and multiply by sigma inverse, and that'll be the identity, right? Okay, but I can also compute it using these guys here. Wouldn't this be tau 1, tau 2 up to tau r times this thing inverted? Do you agree with that so far? And now what would this be? So this would be tau 1, tau 2, blah, 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 tau r. And then this would be Qs inverse, Qs minus 1 inverse, da, 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 Q2 inverse, Q1 inverse. Okay. And now these are all two cycles, right?
Yeah. And if they're the identity has to be.
These are all two cycles.
Okay.
Well, here's the thing. Maybe I haven't convinced you yet, but maybe I should say this first. Qi is a two cycle. So that means Qi squared is the identity, which means it's Qi inverse, right? They are their own inverse. Do you see that? Qi is its own inverse. Right? If it's a two cycle, the square is the identity. So it's its own inverse. So what that means is you have tau 1, tau 2 up to tau r, Qs minus 1, Q all the way down to Q1. The inverse is itself. And now I hope you agree that these are all two cycles. And how many do you have? You have R plus S, right? Do you agree with that? So now, do you see if R is even, since this has to be even, the identity has to have an even number, right? Identity has even number of two cycles. So R plus S is even. And that proves it for you, because if one is even, the other one has to be even for the sum to be even. If one is odd, the other one has to be odd for the sum to be even. Does that make sense? Yeah. And that's pretty much it. Okay. Yeah, we're out of time. But because of that, I can actually say an element is even or it's odd based on the number of two cycle decompositions. So we'll pick up from here and we'll explore that a little bit. Right? I didn't, yeah, the homework, there's no homework that's actually due this week, but you can do almost all the problems that are due, I think. The only thing I haven't defined for you is there's a nice subgroup you can build using the even elements. So, and we'll, sorry? No, there's practice problems. You should do them, but there's nothing that you're going to turn in. Yeah. Just too much grading right now. I can't do it. Yeah. And other homeworks and stuff. So it's good for you guys. But I actually wanted one assignment that kind of combines everything. So